you had to be a good breezy and change your predictions after.
What's the difference between MCMC and variational inference? Why is MCMC called an approximate method? When should we use VI instead of MCMC? These are some of the captivating and practical questions we'll tackle in this episode. I had the chance to interview Charles Margossian, a research fellow in computational mathematics at the Flatiron Institute and a core developer of the STAN software. Charles was born and raised in Paris and then moved to the US to pursue a bachelor's degree in physics at Yale University. After graduating, he worked for 2 years in biotech and went on to do a PhD in statistics at Columbia University with someone named Andrew Gelman. You may have heard of him. Charles is also specialized in pharmacometrics and epidemiology, so we also talked about some practical applications of Bayesian methods and algorithms in these fascinating fields. Oh, and Charles's life doesn't only revolve around computers. He practices ballroom dancing and pickup soccer and used to do improvised musical comedy. This is Learning Bayesian Statistics, episode 90, recorded August 22, 2023.
Let me show you how to be a good breezy and change your predictions after.
Hello, my dear Bayesians. I get a lot of people reaching out for help on their modeling projects, so I have started something new. If you go to topmate.io/Alex_Andora, you can sign up for some one-on-one modeling coaching with me. And each week we'll meet on a live call and I provide you with a step-by-step plan and practical tips to move past these momentary roadblocks. For bigger models, I even have 15-hour and 20-hour packages to make sure my coaching is tailored to your goals and learning style, and also to give you a small discount, of course. So if you feel a bit stuck or lost on your Bayesian project, feel free to check out topmate.io/Alex_Andora, and together we'll make sure to ace your next PyMC model. And now, let's talk MCMC and variational inference with Charles Margossian.
Let me show you how to be a good breezy and change your predictions after.
Charles Margossian, welcome to Learning Bayesian Statistics.
Hi, Alex. Thanks for having me.
Yeah, thanks a lot for taking the time. I'm super happy to have you here. It's been a while since I wanted to have you on the show, and now I managed to find the slots. And thank you also to a few patrons who sent me messages to tell me that they would really like to hear about you on the show. So thanks a lot, folks, for being so proactive and giving me ideas for the show. So Charles, let's dive in, and as
Maybe
usual,
I can bring up a very quick anecdote, which is I think 2-3 weeks ago, your show came up, and I told my colleagues I would feel like I have made it in the Bayesian statistics world if I get an invitation to speak on learning Bayesian statistics. So I'm thrilled to be here, and yeah, thanks for the mysterious patrons with incited this meeting.
Yes, I'm sure they will recognize themselves. So let's start with your origin story. Actually, that's also something I found super interesting. How did you come to the world of statistics and pharmacometrics and epidemiology, Charles?
Mm-hmm. Right. So I became interested in statistics and data as an undergrad. Actually, I was studying physics. I was already in the US. I was at Yale, and I was working with an astronomy lab on exoplanets. And we had a lot of data. So that generally got me interested in data science. But I wasn't introduced to Bayesian methods. And I always was a bit uncomfortable with how we handling uncertainty, what might we do about it. And I was fortunate after I graduated to actually get a job at a biotech company where, so the company was Metrum Research Group. They were based in Connecticut. And the supervisor I got there, William Gillespie, is one of the pioneers of Bayesian methods in pharmacometrics. And so he introduced me to Bayesian statistics, and it made a lot of sense. And I realized, oh, this is what I have been looking for when I was doing astronomy, right? And I started, piecing this together. And to be fair, I hadn't done a lot of statistics before. I don't have the experience of struggling with classical statistics for a decade before being rescued by Bayesian statistics. I encountered Bayesian very early on. But even then, the way we quantified uncertainty, the fact that everything reduced to essentially one equation was extremely compelling to me. And Bill Gillespie hired me at Metrum Research Group to work on STAN. So this was back in 2015, and at the time, STAN was fairly new, very exciting, very promising. And you had these specialized software in pharmacometrics, but they were not open source. They were not really supporting Bayesian statistics, or at least that was not their priority, and they didn't give you the flexibility that a lot of my colleagues were looking for. On the other hand, you had STAN, which was open source, which had great algorithms to do Bayesian modeling, but which lacked a lot of the features required to do pharmacometrics modeling, right? One example was support for differential equation solvers. And all these models are based on ODEs, and at the time, STAN had limited support for ODEs and more generally implicit functions. And then there were some more specialized things like handling, the event schedule of clinical trials. And the project ended up being, we're going to write some general features, we're going to contribute them to STAN, and then we're going to write a specialized extension called Torsten. And that's going to have, more bespoke features targeted at a pharmacometrics audience, right? And so that was my exposure to STAN. I can tell you about my first pull request, which Bob Carpenter and Daniel Lee reviewed extensively. They were very patient with my C++. And my plan, my loose plan, had been, well, I'm going to work, for 1 or 2 years. I'm going to learn programming and statistics because I had gained an appreciation for it in astronomy. And then I'm going to do a PhD in physics. But Andrew Gelman, who I had met in an official capacity, like through my work, encouraged me to apply to the statistics program at Columbia University, saying, if you do statistics, you'll still be able to work on the natural sciences and the physics that you're interested in, but you'll have maybe you'll be able to make a more unique contribution as a statistician. So I took his word for it. And once I had the offer from Columbia, it was a difficult decision, but I decided, okay, I'm going to do a PhD in statistics. And that was a big change of field. But I did pursue that. I was able to continue working on STAN and on STAN adjacent projects. And just a year ago, I completed the PhD. So I would say that's the origin story that eventually led me to the Flatiron Institute. So that's where I'm currently. It's in New York. We're a nonprofit. We focus on applying computational methods to the basic sciences. It's a big emphasis on collaboration. We have people who do astronomy, who do quantum physics, who do biology. And so that really resonates with why I wanted to do statistics in the first place, which I want to solve problems in the sciences.
Yeah, I can really relate to that. That was also kind of what happened to me too. Even though the the first field was political science and not astronomy.
Okay.
But yeah,
Yeah.
like definitely in the end, applying the methods became more interesting than the field in itself. So continued on that path.
Right, and I think that the attitude I had. So I had offers to do a PhD in physics, a PhD in statistics, and a bunch of different fields. And at the time, my attitude was, look, wherever I go, I'm going to have to do, analyze some data, understand where that data comes from. I'm going to have to, have the tools to do the analysis, to do the statistics.
Mm-hmm.
So the idea is, I think our loyalty is not to a discipline or to a field, it's really to a problem.
Mm-hmm.
Whatever problem we work on, there's always a lot that we need to learn. We're never experts in a new problem, in a new research problem. And so kind of like try not to take the field that I'm in, whether it's for the PhD or even right now I'm in computational mathematics, right? Whatever that means. But I care more about the problems I work on than the department I'm affiliated with.
Yeah, completely relate to that for sure. Like the fact of using the method to solve an interesting problem, whether it is about astronomy, political science, biology, epidemiology, it's like, and in the end, I find that even more interesting because you get to work on a variety of topics that you wouldn't have otherwise, and also you learn so much. So that's really the cool thing. Yeah. So thanks a lot for this introduction. And so right now these days you're working at the Flatiron Institute, as you were saying, and it seems to be a very diverse organization. We had Bob Carpenter actually recently on the show, so I'm gonna link to his episode in the show notes. But you, Charles, what are the topics you are particularly interested in these days at the Flatiron?
Yeah, I think that I have a little bit two poles right now. They're a bit on the methodology side of things, and one of them is variational inference, which is a form of, it's called an approximate Bayesian method, is what it's called. And really what I'm trying to understand is, when should we use an approximate method like variational inference? Because it's incredibly popular. It's used in a lot of fields of machine learning. It's used a lot of times in artificial intelligence, and yet you have so many smart, brilliant people who are completely distrustful of variational inference. And it's also not difficult to construct an example where it really doesn't do the job, where it really fails in a spectacular way. And I think that ultimately it depends on the problem you apply it to. And what we need to do is understand, when can we get away with the approximations that variational inference proposes to do? Why does it sometimes work really well? Or why do we sometimes really get punished for using variational inference? And I can give you a very simple example of that.
Yeah.
Which was, so this was a recent work with Lawrence Soll, who is also at the Flatiron Institute. He kind of heads machine learning there. And there's a statement that goes around, which is to say, well, variation inference will give you good estimates of the expectation value for a target distribution. So that's great. We often care about expectation values, whether that's in statistical physics or in Bayesian statistics. But on the other hand, it will underestimate uncertainty. Okay. Well, what does it mean to underestimate uncertainty? Right? How do we make sense of a statement like that, which has appeared time and time again over the last 2 decades? And really, we realized that there were two measures of uncertainty that seem to come up again and again. One is the marginal variances. and the other one is the entropy. And so people like the entropy because it's a multivariate notion of uncertainty, and it's a generalization of the marginal variance, right? So when people say variational inference underestimates uncertainty, they usually mean you're underestimating the marginal variances and you're underestimating the entropy.
Okay.
And so what we ended up doing is demonstrating this on the Gaussian case, right? You have a Gaussian target, you're approximating it with a Gaussian with a diagonal covariance matrix. So that's called the factorized approximation or the mean field approximation. And indeed, you underestimate the marginal variance and you underestimate the entropy. Now, here's where it gets interesting, which is as you start going to higher dimensions, and for some reason, I don't think people have only looked at, really the two-dimensional case, because that's the figure that fits on a page, right? But if you start going to higher dimensions and you take limits where the dimension goes to infinity, you can construct examples where you actually get very, very accurate estimates of the entropy, but you are underestimating the marginal variances in every dimension in an arbitrarily bad manner. And so the two notions of uncertainty are not at all equivalent and not at all interchangeable. And what ends up happening is you look at fields where variational inference is applied. So for example, in statistical physics, where people want to estimate the entropy of an Ising model, for example. And that's where this factorized, this mean field approximation comes from. Okay. Well, here it works just fine. You actually get good estimates of the entropy, right, in certain limits. In machine learning, where you're trying to maximize marginal likelihoods rather than default Bayesians, actually, you get good estimates of those marginal likelihoods. Right? At least that's our working conjectures. But in Bayesian statistics, where we have interpretable quantities, and those marginal variances mean something, or those parameters that have a meaning, well, here variation inference might really not do it, or at least not vanilla implementations of it, right? And that's an example of, how by studying an example, we can start on the understanding why is it that some people are so enthusiastic about variation inference and other people are so distrustful of it, right? It really depends on what is the measure of uncertainty that you care about, and that in turn is informed by the problem you want to solve. Right? So I bring this up as as an archetype of the work that we're trying to do. We want to understand this method, when and why. Right?
Yeah, that's really interesting.
First big topic.
Yeah.
The other big topic is I still do a lot of MCMC. I care a lot about MCMC because, as we'll see in pharmacometrics, I really think that is our best tool to solve many problems. And here I'm trying to understand some more fundamental questions, right? So people often say, well, MCMC is great, but it's too computationally expensive, right? That's why we'll use approximate methods.
Yeah.
And one thing I will argue is actually it's computationally expensive, but we don't really have a very good sense of how much computation we should throw at MCMC, right? Because ultimately we have three fundamental tuning parameters, right? One is the number of chains that we use. Right? The other one is how long is the warm-up or the burning phase, and then the third one is how long is the sampling phase. And actually, it's not clear what is the optimal computation that you should throw at an MCMC problem, right? I think people rely on heuristics. More often, they rely on conventions. These are the defaults in STAN and PyMC and TensorFlow probability. But actually, we need to think about, have we used a warm-up phase that's too long or too short, or a sampling phase that's too long or too short, right? Or how many chains is it useful to do? Especially now we have GPUs, right? In theory, I could run MCMC with 10,000 chains. And people do that now, right? I mean, some people do that. A select few do that now, right?
Yeah.
But what are the implications of doing that, right? I'll tell you an implication. If I have 10,000 chains that I'm running on a GPU, then I think the sampling phase can be one iteration per chain. Right? We can discuss this, and we can argue for or against it, right? But it changes a little bit our perspective of how much computation we throw at it. Another perspective I like is if you have a strict computational budget, and then you say, well, I'm not going to use MCMC, it's too expensive. Let me run variational inference. I know it's biased, I know it's approximate, but at least it finishes running in, within 10 minutes.
Yeah.
I'm like, well, run 10 minutes of MCMC. It'll be biased, it'll be approximate, and it will finish running in 10 minutes. Right? And then ask yourself, well, how good is this estimate? Thinking a little bit more carefully about, how much computation do we really need for MCMC and for the different problems that we might be trying to solve?
Mm-hmm. Yeah, that's really interesting. Thanks a lot for that very clear presentation. I really love it. So let's actually continue on that path because I wanted to ask you about that a bit later in the show anyways. So several things that bumped into my mind. First thing is MCMC is also an approximation method, right? So why do we, and I know we usually do that in the field, we define variational inference as an approximation method, which kind of underlies, assume that MCMC is not, but it is. So can you maybe draw the distinction? What makes the difference between the two methods, and why do we call them approximation for variational inference?
Yeah, absolutely. So I think that people think, like a lot of statisticians, asymptotically, right? So you know that asymptotically, in what sense? When you run a single chain for an infinite number of iterations, MCMC is, not only going to, generate samples from its stationary distribution, which oftentimes is the posterior distribution, but also Monte Carlo estimators with, an arbitrary precision. Right? Your Monte Carlo estimator will converge to the true expectation value or the true variance or whatever it is you're trying to estimate. Right? Whereas with variational inference, here we have to be a little bit careful because, what does it mean for the asymptotic of variation inference? So you might say, okay, I'm going to run the optimization for an infinite number of iterations. So let's assume that the optimizer does converge. And actually, until recently, this was not really shown. There's a recent preprint that I know Robert Gower and Justin Dumke have been working on, where they actually showed that, yes, under certain conditions, stochastic optimization will converge for variation inference. Right? But then even if it doesn't converge, you say, well, let me think about, the approximation that minimizes my objective function. So oftentimes the Kohlberg-Leibler divergence. Right? That's what I get asymptotically. Well, that will still not be, in general, my target distribution. Right? Even asymptotically, I'm still approximate. Right? So I think that's why people draw this distinction between MCMC and variational inference. It's really in the asymptotic sense that MCMC is an exact method, whereas VI remains approximate. Right? Even if you've thrown an infinite amount of computation, that's your problem. Right? Now, in practice, we're not asymptotic, right? We work with finite computation, and so I think it's very important to recognize that yes, MCMC is also an approximate method. It's not unbiased because you don't initialize from the stationary distribution. You do not reach the stationary distribution, right? So when I hear statements like, well, first we wait for MCMC to converge to the stationary distribution. I think people have the right intuition, right? I don't think it's a misleading statement, but nonetheless, it's an incorrect statement. What we do is we wait for MCMC to get close enough to their stationary distribution. And the reason why we care about being close enough to the stationary distribution is because you want the bias to be small, right? And so when we think about, convergence diagnostics, the way I think we we really should start thinking about, a quantity like the R-hat statistics, for example. And R-hat is interesting. R-hat has been around for 3 decades, and frankly, there's still debates about what does R-hat measure. I mean, this is very existential, right? We have an estimator, but it's not clear what the estimate is. And my perspective, my most recent perspective, is that what really matters, the reason I care about convergence is because I want the bias of my Monte Carlo estimator to be sufficiently small. It's not going to be 0, but it has to be sufficiently small. And so can R-hat tell me something about how small my bias is? And here's the paradox, which is that R-hat, the way you compute it, it's a ratio of 2 standard deviations, right? So you know that when you measure variance, it doesn't tell you something about bias, right? And yet, we say R-hat tells you if your warm-up phase is long enough.
Yeah.
Not everyone agrees that that's what it tells you, but, that's my perspective, and I think it's a reasonable perspective, right? But the point of the warm-up phase, at the primary point, not the only point, is for the bias to go down, right? So we're faced with this paradox, this very fundamental question. Can R-hat actually give us any useful information? And there was a recent paper that argued that, well, since R-hat is really just looking at the variance, it's a one-to-one map. So this was some really nice work by so I know Dukida Vats is one of the co-authors on the paper, and there's another co-author, right? They call it Revisiting the Gelman-Rubin Statistic. Mm-hmm. They argue, well, R-hat is just a reframing of variance and of effective sample size, right? And to me, effective sample size only matters when you're looking at the sampling phase, because it tells you, is your variance low enough? And so we had to think a little bit hard about this, because it wasn't completely satisfactory, because either it means that R-hat is not a useful convergence diagnostic in some sense, or actually there's more going on. And what we realize is you look at the variance that's being measured by R-hat. So really what R-hat ends up measuring is you're running a bunch of chains. It could be 4 chains, it could be more. Each chain generates one Monte Carlo estimator, and then you average the per chain Monte Carlo estimator. So now you look at the variance of a single chain Monte Carlo estimator. That variance, you can actually decompose it into a non-stationary variance and a persistent variance. And what we realize, and you have to be careful, you have to do that analysis for non-stationary Markov chains. Otherwise, you completely miss the non-stationary variance. Mm-hmm. And the non-stationary variance is, actually, it's a measure of how well you've forgotten your initial point. Mm-hmm. And you can show in some cases that it decays at the same rate as the squared bias. So you're not directly measuring the squared bias, but because MCMC is what it is, the non-stationary variance gives you a proxy clock for the bias. And so our argument is that, well, what's interesting about R-hat is not that it measures, the persistent variance, which you can then relate to the effective sample size, but that it measures the non-stationary variance, right? And this then led us to, we're coming up with revisions of R-hat, which more directly measure the non-stationary variance rather than the total variance, so that we actually get an estimator that unambiguously tells you something about the length of the warm-up phase. And then you ask the question of the length of the sampling phase in a second and separate step. So, it's a conceptual explanation. So that this is a paper that we have a preprint out. It's called the Nested R-hat. Mm-hmm. And this is joint work with Andrew Gelman, Aki Vettari, Matt Hoffman, so some of the usual suspects. We also have Pavel Zuntsov and Lionel Riou-Durand. Mm-hmm. So we've all worked on this together. And a cool anecdote here is that what we were really interested in is those regimes where we're running hundreds of chains in parallel or thousands of chains in parallel, like GPU-friendly MCMC. And what this made us do is instead of taking asymptotics in the limit where we have an infinitely long chains, which is how asymptotics for MCMC have worked for the past, 5 or 6 decades, right? Because that's what people did. They ran long chains, right? And so even though asymptotics are a property of, infinity, we want to somehow get close to asymptotic regime, right? That's why we care about this asymptotic analysis. And here we thought, well, let's take asymptotics in another direction. Let's say we have a finite number of chains, but what happens when we have an infinite number of chains? And then suddenly you can do asymptotic analyses on non-stationary Markov chains, right? So the problem is if I take an asymptotic in the length of the chain, well, I've made my chain stationary, and then there are only so many properties that I can study. If I take asymptotics in the other direction, which is the number of chains, then suddenly I can start making statements about non-stationary Markov chains. I can elicit terms such as, non-stationary variance. And this was a cool example where the hardware, trying to work with, GPUs running a lot of chains, actually, I think is really changing our theoretical approach and our conceptual understanding of MCMC. And I think we're going to get a lot of breakthroughs from this kind of perspective.
Yeah, super interesting. I put the 2 papers you mentioned in the show notes, and so that makes me think. Basically, what would you say right now, practically for people? When would variational inference usually be most helpful, especially in comparison to MCMC?
Yeah, so great. So I think there are 2 things to unpack here. One is, when can variational inference still give you accurate answers? And 2, when do you actually not need an accurate answer? Right? So in the first question, it really depends on the family of variational inference that you're willing to use, the family of approximation, and also it turns out the objective function. So I mentioned earlier that when I have this mean field approximation, and I'll just remind what mean field means is I'm assuming that all my latent variables are independent. Now, we don't believe that that's true in practice, but that makes the computation much cheaper. And when you have millions of observations, millions of parameters, you need an algorithm where the cost scales linearly with the number of observations. And if I don't have this mean field assumption, I get things that can scale quadratically or cubically, right?
Yeah.
And so when I do this approximation, well, I'm going to get some things wrong, but maybe I'll get the things that I care about right, which could be, the first moment, or it could be the entropy, right? If you change the objective function, so actually the KL divergence, you can kind of reverse it. You can show that you get arbitrarily poor estimates of the entropy, but good estimates of the marginal variances, right? So it turns out that the choice of objective function that you use to measure, the disagreement between your approximation and your target matters. So there's a real question of, what are the quantities you care about? Because we don't care about the whole distribution. We care about some summaries of the posterior distribution, right? And then that informs when you use them, right? So I think that's the first question. And I want to emphasize that there's a lot of great work by, Tamara Broderick and her group, Justin Dumke and his colleagues about, trying to get more accurate variation inference. And sometimes that works really well, which is a bit of, I can't really give you a more precise prescription than that because we have to go into the details of, the different problems, right? But then the second point I made is sometimes you don't need a really accurate answer, right? So what are examples of that? So, so in machine learning, let's say you're just training a model, and maybe you're more interested in a more, either a more complicated model or using more data than improving the accuracy of the inference. And then you look at something like, performing a task, classification, prediction, and so forth under a computational budget, right? It turns out that it's better to have a sophisticated model with very approximate inference than a less sophisticated model with more accurate inference.
Mm-hmm.
Now, it's hard to know, my big problem with variation inference is it's hard to know which regime you're going to be in and to actually justify it. And even once you've run variation inference, you don't have that many diagnostics that can tell you, well, you're doing okay, but you would do much better if you improve the inference, right?
Mm-hmm.
So I think that it's an open question. But then the other example where, that I want to bring up where we don't always need accurate inference is when we're developing models, right? So this ties back into this idea of the Bayesian workflow that now has been championed. So Andrew Gelman and colleagues wrote a lot about it. Michael Betancourt wrote a lot about it. David Bly wrote a lot about it. Arguably George Box, right, wrote a lot about it. And if you ever work on an applied project, you sit down, you come up with the first iteration of your model, and arguably there are a lot of problems with that model. And you don't need super accurate inference to diagnose the problems with this model. You do a quick fit, a quick approximation, and usually something obvious is gonna pop up. Mm-hmm. Then you revise the model. Then you do again quick inference, okay, and you keep refining and refining. And only once you have actually a polished version of the model do I think that it makes sense to get out the big gun and the very accurate inference. Right? And I think that if we talk about pharmacometrics and epidemiology, I'll give you some very precise examples of those situations.
Yeah, for sure. We'll do that in a few minutes. But yeah, thanks a lot for that tour. That makes a lot of sense, actually. All of that. I will use.
I realize my answers are very long, but your questions are very deep. So
yeah. No, that's really good. I mean, that's why the podcast is for. Also, going deep into the explanation that you cannot really do in a paper, right? In the papers, usually it's a more technical audience first, and so you're not gonna really explain the difference between variational inference and MCMC in a paper, because if the audience already is supposed to know that, well, why would you do that in a paper?
So. Yeah, and frankly, the paper. So what ends up being the discussion that ends up being in the paper is usually the discussion you've had with the reviewer.
Yeah,
which is a subset, which is really a subset of everything you would like to discuss. So it's nice to have a more free format. To really think about those questions. And what I will say is that actually the one format that I really like where all these questions come up is is teaching, is like workshops.
Yeah. Mm-hmm.
And so when you do a workshop on Bayesian modeling, you do a workshop on STAN, IMC or something like that, all the questions that I've brought up, how long should the sampling phase be? How long should the warm-up phase be? Should I use this or that algorithm? Those are questions that a person sitting at a workshop, intro to STAN, intro to, your favorite language, would ask. And so these end up being forums where, we do discuss these fundamental questions, because even though they're deep, they're elementary nonetheless. And I mean that in the most positive sense of the word elementary possible.
Yeah. No, completely. You have completely outmasked the way I pick questions for the show. It's just doing the same as you did. I teach a lot of workshops too, and these questions are basically the questions that a lot of beginners ask, where it's they often have used variational inference because for some reason, especially when they come from the classical machine learning world, then using variational inference makes more sense to them because it's closer from home, basically closer to home. And so, and then the natural question is, when should I use variational inference? Why should I use it? Why should I even bother with MCMC? Things like that. So a lot of the questions I've been asking.
And these are totally open questions. I mean, correct me. Maybe you have an answer that I missed, but we have heuristics and we have good pointers and we have good case studies. But so much of this remains unanswered. I think.
Yeah.
Not unapproachable. Let me be clear. Totally approachable, and you can, it's not crippling. We can totally still do Bayesian modeling, but there are open questions that linger.
Yeah. And then you have to strike the right balance between when you're answering such a question from a beginner, where you want to be like intellectually honest and saying, yeah, like these are still open questions, but at the same time, you don't want to them to walk away with the feeling that, well, this completely undefined, and I cannot really use these methods because there is no clear rule about what I would use and when and why. So like that's always an important balance to strike, and not always an easy one.
Yeah, I absolutely relate to that.
Yeah, so actually, before we dig into a bit more of the applications, I'm curious basically on the work you're doing right now, because I really love the fact that you're both working on MCMC and on approximate Bayesian inference. So I'm wondering, what are the frontiers currently in that field of algorithms that you find particularly excited about? You already mentioned basically the progress of the hardware, which opens a lot of avenues. I'm curious if there are other things you have your eye on.
Yeah, I think that I think hardware is an important question, and I think it's a difficult question. And I want to talk. I think maybe I want to say a little bit more, because I think frontier is good, and not only that, I think it's an ambiguous frontier, because I don't think to me it's not clear how much we're going to get out of hardware for MCMC, for example. And what are going to be the limits of that, right? And so what I'm excited is that now we have GPUs. Now we have several algorithms that are GPU friendly. And I'll explain a little bit what that means, but essentially, at a very fundamental level, what it means is you can run a lot of Markov chains in a synchronized time. And so you're not waiting for the slowest chain, basically. That's kind of the intuition here.
Yeah.
And people are like, well, this is great. If we run a lot of chains, we can really make the sampling phase much shorter. Like again, let's say your target effective sample size is 2,000. And actually, what effective sample size you should target, that's another interesting and very fundamental question. And it turns out a question where different people have different opinions on within the Bayesian community. But let's say now, for sake of argument, you're targeting an effective sample size of 2,000. And I'm not saying this is what you should do or not do, but let's just say 2,000. Then once you run 2,000 chains and you warm them up enough, right? Well, really, you only need one good sample per chain, which means your sampling phase can be one iteration. And then all your questions about how long should the warm-up be, it's no longer about, adapting the kernel so that I have a low autocorrelation during the sampling phase. Actually, the autocorrelation only matters insofar as it reduces your bias, right? And so I think that suddenly we've greatly simplified the question of diagnosing, how much computation we need to throw at the algorithm. If we have a lot of variance, then suddenly it just becomes about bias decay, and the sampling problem becomes much closer to the optimization problem, right? And then I can go into questions. So then there are interesting things where you actually run a lot of chains. You can pool information between the different chains to make the warm-up phase shorter. And for some problems, like you have these multimodal problems, like it's exponentially shorter. Like you're never going to get a good answer with a single chain that doesn't use cross adaptation, right? And so here I want to give a shout out to Marie-Lou Gabriel and her work on MCMC that uses normalizing flow for adaptation, right? That's a thing. That's a technique where they actually, run 10,000 workers or chains. And I remember when I was talking to her and colleagues, I was like, well, once you're already running 10,000 chains to jump between the modes, you actually don't need a long sampling phase at all, right? Yeah. So that's one aspect of it. But then even for more ordinary problems, you can show that the time it takes you to reduce the bias goes down with the number of chains because you are pooling information between the Markov chains. And this is not something that we really understand. And so, where I see the frontier is that actually, if I run a lot of chains, I also get more accurate diagnostics. My computations of R hat and its generalization become much more reliable. And I think the holy grail would be something where we don't have users specify the length of the warm-up phase or the length of the sampling phase. We have them think about what is your target ESS, that's the number of chains that you run, and then we're going to automatically stop the warm-up phase when we hit a certain target, right? And then suddenly, we're starting to do optimal computation for MCMC. And I think that to do optimal computation, at least in the way that I've described it, we need those GPUs. And at the same time, I think that there are a lot of problems that are not going to be amenable to GPUs, right? There's still this fundamental sequential component, which is, the bias has to go down, the warm-up needs to happen, right? At some point, adding more chains is not going to help you, right? Whether the speed up you're going to get on this is not going to be arbitrarily large, right? And then, the benefit you're going to get from variance reduction by running more chains, well, if your target ESS is 2000, maybe it doesn't help to run 10,000 chains, right? Or at least not immediately, right? So those are very clear, questions that arise about, ultimately, how far are we going to be able to go with running many chains. But what I want to emphasize is that there's a computational gain, which people think about. Our algorithms are faster. But I also think there's a conceptual gain. And there is the opportunity to make MCMC more black box. And what I mean by that is we're less reliant on some very fundamental tuning algorithms. Right? And therefore, we kind of get into this regime where the computation that we're using is just the right amount. Yeah. And that's really, if I have to say, like I have another 1 or 2 years as a postdoc, very optimistically, that's a problem I'd like to solve. Right? Like we remove the fundamental tuning parameters of MCMC. And there are other approaches towards that. Anyway, I'm not going to pretend that this is the only angle to tackle this problem. Let me be absolutely clear. But I think it's a very, very promising.
Yeah, for sure. That's fascinating.
What I will say is, since we're going to go into applications, is one limitation with GPUs is they're very bad at solving ODEs. And a lot of the problems that I care about, have likelihoods. And in order to evaluate those likelihoods, you need to solve an ODE, right? So, I don't think we're at a stage where running 1,000 chains on a GPU is going to solve all the problems in pharmacometrics that I am, deeply invested in, right? That said, we have clusters of CPUs where maybe we can run 60 to 120 chains, and that can get us some of the way.
Yeah. I mean, when you were talking about that, I was thinking that'd be super cool to have, in Stan or PyMC afterwards, like at some point, automate away the number of chains and samples that are taken instead of having them, because right now it's like, okay, we're going to run as many chains as we can with the GPU or CPU we have. So that's already kind of automated. But the number of samples not really automated. Is like just a rule of thumb where it's like, okay, we think in general, these number of samples work well. In PyMC, it's 1,000 per chain. After warming up. But like what would be super cool is like, okay, like PIMC or Stan, see what's there, the resources, and then it's like, okay, so given the complexity of the posterior that we can see right now, like we are going to run that many chains and that many sample per chain. That'd be super cool, because also that would be something that would be easier for the beginners, because they are really sometimes very anxious about having a lot of samples, even though no, you don't need 10,000 samples for that per chain for that simple regression. But it's hard to explain.
Yeah, and so what ends up happening, very real experience, and I do it myself, is the simple models that probably don't need that many iterations. I run them for a lot of iterations because that's computationally cheap to do.
Yeah.
And then the hard models, where each iteration is very expensive and the posterior distribution is much more complicated, I actually end up, and where I would need more iterations, I end up running less iterations.
Yeah.
Right, and I think a lot of people will sympathize with that. That's my experience interacting with practitioners. I'll give you another example of things I've seen my colleagues in epidemiology do, is that when their model starts getting really complicated, they start using somewhat less over-dispersed initializations.
Mm-hmm.
Even though we know that that's what we need for the convergence diagnostic to be reliable. And I'll tell you a little bit more about that, because actually that's another question. It's like, what does it mean for an initialization to be over-dispersed? And I have some answers to that are not quite, the regular answers. But that's a huge problem. Like when models get hard, and again, those ODE-based models, right? You cannot solve those ODEs if you throw insane parameter values at your model, right? And so now people have to make compromises, and I think that especially statisticians, we're a little bit cavalier. We tend to be conservative, because maybe in a way, that's the role of the statistician and the theorist, is to be conservative and to play it safe. But when the safe and the conservative heuristics become impractical, we need to think harder about, okay, if we don't want to be too conservative, but we still want to be safe, what do we need to do? And that's where these questions of, optimal warm-up length, optimal sampling phase, optimal over-dispersed initialization really come into play. Because if you're too conservative in your prescriptions, you might make your editor happy, but actually practitioners are going to have a really hard time following those prescriptions.
Yeah.
And then they do things. I'm not saying that they do silly things instead, right? But they do other things that are maybe less principled.
Yeah, fascinating. Could spend the whole episode on these topics. I really love it. Thanks a lot for diving so deep into this, Charles. Let's get a bit more practical here and talk about what you do basically with epidemiology and pharmacometrics. So first, can you define pharmacometrics for us? I personally don't know what that is, how that differs from epidemiology, and what do Bayesian statistics bring to epidemiology and pharmacometrics?
Yeah, so pharmacometrics, the way I would think about pharmacometrics is to pharmacology what econometrics is to economics. Some people who want to emphasize that they're using quantitative methods. Right? Now, the particular field of pharmacometrics that I've worked on is called PK/PD modeling, so pharmacokinetics and pharmacodynamics. And essentially, what happens is, let's say there's a new treatment that's being developed. So it could be a new drug compound, or it could be a number of things. We're usually interested in two questions. Is one, how does the drug get absorbed and how does it diffuse in the patient's body? That's called the pharmacokinetics. And two, once the drug diffuses in the body, what does it do to the body, right? And so that includes, targeting a disease, but also side effects. Right? We're always worried about, how toxic a treatment might be. And what people are trying to do with these models is based on early data from clinical trials, so either on human beings or even on animals. They try to predict what is going to happen when we look at a broader population of individuals and when we kind of like start changing the treatment. So you have some medical treatments can get very complicated. You have questions of, I have a certain drug compound. How much do I administer? How often do I administer it? Is it better to take, half a dose every half hour or only a single dose every hour, right? And so you have all these, combinatorics of possibilities. If I really increase the dose, do I immediately get better effects, or does it kind of saturate, right? We often have these nonlinear effects. They're called Michaelis-Menten models, where at some point, right, adding more dose erases the cost and it doesn't help the patient, right? Yeah. And one way to do it would be, you run a ton of clinical trials and then you hope that something works out, and that's extremely expensive and time consuming, and maybe it's safer for the humans than the animals. Let me put it this way. Or you based on a bit of data, and then a really mechanistic model where you actually really bake in some of your expertise as a pharmacologist, as a biomedical engineer. You try to understand the underlying system so that when you're trying out different regimens, you can really predict what are going to be the doses that are more promising. So it's very useful to do exploratory analysis. And then it's also useful to do, once a drug hits the market, you actually collect very imperfect data, you actually have uncertainty, but you still want to keep learning about the dose and the dosing regimen, right? From data from hospitals. And sometimes the data is rare, you have rare diseases, rare conditions, and that kind of thing. Right? So that is, if you will, the domain of pharmacometrics.
Yeah.
And what's extremely interesting is that within that domain, you have, so first of all, you have what's called mechanistic models. And what I mean by that is the parameters are interpretable. The relationship between models is interpretable. I'd contrast that with a neural network, for example, where I might get good predictions. But then if I want to do out-of-sample predictions, which is actually really what we want to do, right, in pharmacometrics, right? Examples of out-of-samples would be a different dosing regimen, or I've tested the drug on an adult population. What happens if I do it for children, right? That's the kind of pediatric questions. Right? We need to bake in the mechanistic understanding, which doesn't exclude a role in neural networks. I think these can also play a role, but I'll leave that for now. But then you have various degrees of details in the mechanism. You have some equations that are very simple. So a two-compartment model with first-order absorption says the human body is three compartments. There's the gut, where the drug arrives when you orally administer it. There is the central compartment, where the drug diffuses quickly. So usually that includes the blood. Right? And then maybe there's a peripheral compartment, so tissues, where the drug diffuses more slowly. Right? That's obviously not a very detailed description of the human body. And then you have models that are more complicated. So at Metrum, Matthew Riggs and some colleagues, they work on this bone mineral density, where actually they had a lot of different parameters. And now instead of having a system of 3 differential equations, you have 30 differential equations. You have a ton of parameters, but you have a lot of information, prior information about these parameters. And then you have people who, really throw, differential equations with hundreds of states at them, and thousands of interpretable parameters. And frankly, I don't think we have the Bayesian computation to fit those models. even though in theory they lend themselves extremely well to a Bayesian analysis, right? I think that realistically we're somewhere in the semi-mechanistic regime. So these are models that have some level of sophistication, but already we pay a dire price for this sophistication, which is that the computation can take hours or days to fit, right? And so there's like really this potential for, like better Bayesian computation can really allow people to deploy better models and more sophisticated models. The other big aspect of pharmacometrics is usually we have trials with data from different patients. There's heterogeneity between the patients, there's similarity between patients. So that lends itself very well to hierarchical modeling.
Yeah,
and hierarchical modeling is hard, right? It tends to create these posterior distributions with geometries that are very frustrating. And I spent a lot of time worrying about hierarchical models. I've done a lot of work on nested Laplace approximations. So that's another nice example of an approximation. It's not variational inference. It has very complementary qualities. And what the nested Laplace approximation allows you to do is marginalize out the latent variables in a hierarchical model, right? And people often explain nested Laplace as, oh, it's great, it reduces the dimension of your problem, right? And then we can throw a quadratic at the remaining parameters. We've had models where we had thousands of hyperparameters. Those were genetic problems where we were using horseshoe priors to select genes. So even once you marginalize out, the latent variables, you still have a high dimensional problem. So we threw Hamiltonian Monte Carlo at it. But it still made a big difference because we simplified the geometry of the posterior distribution by doing this marginalizations for the hierarchical models, right? So I'm very excited about the prospect of having, a nested Laplace approximation in STAN. We have a prototype that works really well. We have some really cool automatic differentiation supporting it. But the problem is, again, I want to try this on ODE-based models. I don't get a good approximation. I don't get efficient automatic differentiation. I get something that's unstable. Now, the simple examples where I got it working, it actually gave surprisingly accurate results, right? But this is, again, an example where here's this awesome algorithm and statistical methods, and it just gets frustrated by the nature of the problems we encounter in pharmacometrics, right? Even though, these are hierarchical models and these methods are designed for hierarchical models. But again, if your likelihood is not a general linear model, suddenly those approximations become much more tricky. And that's why, I think that we have to use MCMC for these models.
Yeah, that's interesting. So in these cases, that makes it a bit clearer, I think, for people in the practical cases where you would have to do that trade-off, basically. How do you choose between the trade-off between the different methods? I think it's very important.
And that said, I do want to say that there's some really cool approximations that people do deploy in pharmacometrics. I recently read I'm an anonymous reviewer, so I'm not going to give out too many details.
Sure.
But what I liked, there were questions of what if we fix those parameters, or what if we draw these parameters from their priors because they're removed away enough from the data that maybe they're not influenced that much by the data. So the posterior stays close to the prior, but nonetheless, we need that uncertainty for the interpretable quantities in the middle, right? And so people are coming up with these compromises. And of course, now we're again in the business of we have these awesome computational constraints. People come up with these approximations, either of the inference or even, they say, well, let's use a simpler model. Like, we know there's a more complicated model out there, but maybe we still get all the answers that we need with the simpler model, right? And so now we get again in this, the question of understanding what are the simplifications that we get away with, what are the ones where we pay a heavy price? Can we actually quantify the price we're paying? Can we diagnose when the simplification is too dire or not? And as far as I can tell, the answer is, we're not at the stage of diagnosing the problem. But at least now people are taking this problem seriously enough that they're building these case studies. Now, based on these case studies, where we do try out the different models and we do fit the complicated methods, and we're able to say something about the simpler methods because we did fit the complicated methods. So it's an academic exercise in a way, but at least it gives us, that's how it starts, and that's how we're going to start developing the intuition and the heuristics to then deal with deploying the approximations and the simplifications in practice.
Yeah, that makes sense. And so actually, do you have an example of a research project that where you applied Bayesian statistics in this field of pharmacometrics, and where really Bayesian statistics help you uncover very important insights, thanks to all those methods that you've talked about?
Yeah. So I've never led a project in pharmacometrics. I've always collaborated with pharmacologists. And it's true that my work has been more methodological, has been more developing Torsten itself. That said, what I can talk about is some of the interactions I've had with pharmacometricians, and some of the works where maybe I'm more a contributor than, say, the project lead. And I'll give you one example, and then I think that if we have time and we talk a little bit about epidemiology, I have a very good example in epidemiology.
Okay. Awesome.
But this was super cool, actually. This is a bit anecdotal. I don't know that there's a preprint on this now, but I was in Paris. I was visiting the INSERM, which does a lot of medical work, and I was visiting France Montré's group, and they have fantastic people there. And I'm talking with Julie Bertrand, and she's interested in pharmacogenetics, right? So where we have some genome sequencing or some gene tracking that's involved, and we're trying to see how a patient reacts to a treatment, to a certain condition. And in that case, what ended up happening, so one of the things that was frustrating is they're trying to identify what are the genes that are meaningful, that seem to have a meaningful connection to the outcome of the treatment. And they couldn't get anything that is statistically significant, in the traditional sense, right? There wasn't one gene or one SNP that unambiguously stood out as, yes, this is a meaningful SNP and it should intervene in earlier analysis, right? And what they had done was a Bayesian analysis where they had used a horseshoe prior. And so what the horseshoe prior does is it does, like, it's a regularization tool that does a soft selection, right? And the way that soft selection manifests is there is a quantity that you can look at, and it will usually be bimodal. And one mode will indicate that the covariate that corresponds to this SNP is completely regressed to zero, right? So that's an indication that this is not a very useful explanatory variable. And then the second mode tells you, actually, this variable matters, and it's not regressed to zero, right? And so why are there two modes is because there is uncertainty. But the very cool thing is that even though there was no single SNP that stood out as this is the meaningful SNP, you had two SNPs that came up, and they both had a bimodal, right? So what that means is you couldn't definitely say that either SNP mattered, right? But you can say, okay, with some probability, either of those SNPs can matter. Here's where it gets very interesting, is that actually, because you have a multivariate posterior distribution, you can go a bit further, and you realize that the two SNPs are anti-correlated. right? And so what that means is when you have a lot of posterior mass at one mode for one SNP that says this variable matters, don't regress it to 0, the other covariate would always get regressed to 0. And vice versa, right? So what the multivariate analysis tells you, and what this proper treatment of uncertainty tells you, is like, yeah, you can't, say that, one SNP is statistically significant in the traditional sense, but now you have this more comprehensive treatment of uncertainty that tells you, but you know what? It has to be one of those two. You can't tell for sure which one, but it has to be one of those two, right? And that's a nice example where, we're really, not just looking at the maximum likelihood estimator or even the expectation value or just the variance. We're really looking at essentially the quantiles, the extreme quantiles of the posterior distribution. We're looking at multiple variables and the uncertainty across those multiple variables, right?
Yeah.
So I think that's a very neat example, and a paper to look forward to when it comes out. Or again, this was anecdotal. This was a conversation in the laboratory. But I got very excited about that example.
Yeah, I mean, that sounds super exciting. Thanks a lot for sharing that. And yeah, like if when the paper is out, please get in touch, and then that'd be a fun thing to talk about again. And actually, so we're running a bit long, but do you still have a few more minutes? Because I still have a few questions for you, or you want to close out?
I can stick around for a bit. Yeah.
Okay, awesome. Yeah. So I'd like to talk to you about priors, and then maybe Thorsten or an epidemiology example, or both if time. So yeah, maybe basically you have been working on Thorsten, which is, if I understood correctly, pharmacometrics application of STAN models. So that was interesting to me because the Bayesian field has been evolving really, really fast lately, especially with the new techniques, the new software tools, and you've definitely been part of that effort, Charles. So I'm wondering if there are any recent developments that have particularly excited you, especially in your field of pharmacometrics and epidemiology, and also in relationship with what you're doing with Thorsten.
Yeah. Okay. So let me talk about. Let me give one example. Right?
Yeah.
So not a comprehensive answer, but an illustrative answer.
Yeah, it's great.
And so one fundamental, yet another fundamental question that would come up at a workshop is, okay, I have this ODE integrator, right? I need to solve an ODE to evaluate my likelihood, and the ODEs come with certain tuning parameters. In particular, what is the precision with which you should solve your ODE? And that is going to have an impact on the quality of your inference and also the runtime, right? Because if you solve the ODE with a very strict tolerance, it takes much longer to solve that ODE, right? Yeah. And so again, that comes back to the question of how much computation should we throw at the problem. And for the longest time, I didn't have a good answer, and maybe I still don't, to that question. And the way this manifested is either at workshops when teaching the subject, but even when we were writing the STAN manual, we have a page on ODE integrators. We state these are the default values that we use, but we don't have any clear recommendations on what is the precision you should use. And we kind of assume that the user knows their ODE well enough that they'll know which ODE integrator to pick and what tolerance to set. Which is not realistic, right? But it's just we didn't have an answer to that question, right? And so recently there was a paper, and so I know that. Let me look up exactly who I know Aki is a co-author on it, Aki Vatari. But I wanna give a shout out to the lead author.
Yeah, for sure. And we'll put that also in the show notes for this episode.
Yeah, so there you go. So Juho Timonen is the lead author, and then there are a bunch of other people on it. So their paper is an important sampling approach for Bayesian ODEs. And so essentially, what they realize is, when you're using a numerical integrator to evaluate your likelihood, really you're not computing the true likelihood. You're computing an approximation of this likelihood. And we have a lot of tools in statistics when we're not dealing with the exact likelihood, but some approximation to this likelihood, notably in the field of importance sampling, right? And what they came up with is a way to use those tools that exist in importance sampling to actually check whether the approximate likelihood and therefore the tuning parameter of the ODE integrators are precise enough or not, right? And so that gives you a diagnostic that you can use. It's not a completely perfect diagnostic, and I think I'm still trying to test that idea and play around with it and see how well it really works. So I want to try it out on pharmacometrics problems. Right now I'm writing. I've been tasked with writing a tutorial on Torsten. So we released part 1 a while ago. Now we're writing part 2, and we promised that in part 2 we'd explain how to tune the ODEs. Except we only know so much how to tune the ODEs. So I am trying this method. on the ODEs, but it's just getting me, thinking about, are the tolerances we're using too conservative? Are they too strict? Do we actually get important speedups? And I'm teaching a course this September in Leuven for the Advanced Summer School on Bayesian Methods, where I'm going to have the students on an epidemiology problem, on a pharmacokinetic problem, try out different tolerances and see the differences, and then build this diagnostic that's based on importance sampling to check whether the precision with which they're solving their ODEs is making meaningful changes to the inference, right? And so again, I think that this is one tuning parameter where either we're using ODE solvers that are not precise enough or ODE solvers that are too slow. We're not being optimal in our computation, and this is preventing us from either getting accurate answers or deploying models with the sophistication that we would want to use. So that's a development that I'm excited about. The one caveat that I will throw in this is that right now we're still thinking about it as a single tuning parameter, when what I've observed in practice is that the behavior of the ODE can change widely depending on where you are in the parameter space. So for certain parameter values, you don't need to be super precise. And for other parameter values, you need a lot more precision, or you need a different type of integrator because the ODE just behaves in a different way.
Yeah.
Now, very concretely, how does this manifest? So I don't want to say it's hopeless, but what ends up happening is during the warm-up phase, right, where we start the Markov chains far off in the parameter space, or we haven't tuned the MCMC sampler, so the Markov chains are still jumping left and right. During the warm-up phase, we are more vulnerable to those extreme parameter values. Whereas during the sampling phase, we get away with less strict ODE solvers. So I think that somehow, what I would like to do is two things. One, I would like to have a very automatic way of running these diagnostics in Torsten. And I also want to give users control over what ODE solver do they use at different stages of MCMC?
Mm-hmm.
Because I think that makes a crucial difference. Another way to approach this problem is coming up with good initializations. Right? If I can start my MCMC near, within the parameter space where I might land from the stationary distribution, and I know that here the parameter values are a bit less absurd, and so solving the ODEs is a bit more feasible computationally. If I can start there, then maybe I'm skipping the early regions that really frustrate my ODE integrator and my MCMC sampler. And the way this manifests in practice is you'll have, let's say you run 8 chains. You have 6 of them that finish quickly, and then you have 2 of them that are lagging because they're stuck somewhere during the warm-up phase. They're encountering this region where the parameter values are a little bit absurd. Your ODE is super hard to solve, and that's eating up all your computation. And the truth is, at least in the way we do things right now, we always wait for the slowest chain, which, by the way, we don't have to do, right? So I'm excited about methods to come up with good initializations. And I think that this is a place where variational inference can be good, right? So especially now the Pathfinder variational inference, right, was originally designed to produce good initializations for MCMC. And so getting good initializations, that's a great example of I need a good answer, but not a super precise answer, right? And so, if somehow Pathfinder can help me skip the regions that frustrate ODE integrators, I think that's a big win for pharmacometrics, right? Again, that's something we have to test and really try out. But I will say, now going back, I'm going to make another connection back to R hat, which is when we think about over-dispersion, really what over-dispersion means. So we have shown a bit formally that what makes R hat reliable, and we define reliability in a formal sense, is the initial variance has to be large relative to the initial bias. Now, if you have an initialization, like, you draw your sample from your prior, and that's reliable, and then you throw variation inference, right? If variation inference reduces your squared bias more than it reduces your variance, it turns out you preserve the property of reliability. So there's actually a sense that we might be able to get good initializations for MCMC without compromising the reliability of our diagnostics for convergence, right? And these are all the pieces that I think can come together and really help a great deal with, pharmacometrics, but more generally with ODE-based models, and even more generally, models based on implicit functions. And I do include things that use nested Laplace approximations in that, because that's an optimization problem. That's an implicit function. It has the same kind of misbehaviors that an ODE has, but also technologies that we develop for ODEs in a Bayesian context, better initializations, different tolerances, important sampling corrections would apply to nested Laplace stuff. Right? So those are the things that I'm excited about. But it's going to take time.
Yeah.
I just want to be perfectly honest. Huh? It takes time to really, between the paper and the software implementation and the, clear description in the manual that the users can follow. It takes a lot of time.
Yeah, for sure. I mean, that stuff is really at the frontier of the research. So it does make sense that it takes time to percolate from how to find the solution to, okay, this is how we can implement it and reproduce it reliably.
Yeah, exactly. And I'm most concerned about how speculative I am for some of the ideas I'm sharing. But I think these are directions where it's worth pushing the research. That has the potential to have a really big impact.
Yeah, for sure. And so I put in the show notes the Pathfinder paper, actually. That made me think that I should do an episode about the Pathfinder paper, basically what that is about and what that means concretely. So I'll try to do that.
And if you haven't reached out to Lu Zhang, first of all, the paper is great. But actually sitting down and discussing this with her, at the blackboard or whatever, like, she has so many ideas that have not appeared in the paper itself. So I think, if I can recommend a guest, if you haven't had her already, I don't know if you, but yeah, Lu Zhang, I think would be fantastic to interview.
Yeah, exactly. I was actually thinking about inviting her on the podcast to talk about Pathfinder, because, well, she's the lead author on the paper, and also all the other authors have been on the show. Bob Carpenter, Andrew Gelman, Aki Vetari, so Lu Zhang is missing, so definitely need to correct that. So yeah, in the near future, I'll definitely try to have that episode. That be a very, very interesting one. So maybe can you talk, Charles, about so I'll give you two avenue, and you pick the one you prefer, because I don't want to take too much of your time, but basically I'm curious either about hearing an example of your work in the epidemiology field, or you can talk a bit more in general about a very, very common question that students always ask me, and it's about priors. So basically, how do you choose the prior? How do you approach the challenge of choosing appropriate prior distributions, and especially when you're dealing with complex models? So these are the two avenues I have in mind, and feel free to pick one or pick both.
So let me say that about priors, I think that I want to get better answers. Better answer to this question, and the next time workshop that I'm giving, I don't have a module on priors that I find satisfactory, and so I'm still undergoing this journey. But what I will do is I'll talk about epidemiology, and I will talk about the prior that we use there. And so that will be an example. And I like to think through examples. I like to think through the anecdotal, as complementary to the formal, right? I'm a big fan of fairy tales and fables, simple stories that have good themes. So what happened in epidemiology, and this will be a good example, is the pandemic happened, and suddenly COVID, we're all going home, and we had colleagues in epidemiology, in particular Julien Rioux. So I actually met Julien Rioux at a StanCon. He was in Cambridge. He was a PhD student at the time, and he demonstrated his model, and he was using those ODE-based models. So now, instead of having a drug compound that flows between different parts of the body, what you have is you separate the population, the human population, to these different compartments. So susceptible individuals, infected individuals, recovered individuals, and then the individuals flow between the compartments. Right? And there are a bit more layers. But basically, the mathematical formalism that I had familiarized myself with in the context of pharmacometrics turned out to be very relevant to certain classes of epidemiological models. And essentially, Julien was working on an early model of COVID-19. They were trying to estimate the mortality rate. There was a lot of uncertainty in the data. There were a lot of things to correct for, right? So, for example, early on, not everyone got tested. And testing was not widely available, right? Who got tested? The people with severe symptoms, right? So now if you think about, you're trying to estimate the mortality rate. And according to your data, the people who catch the disease are only the ones who have severe symptoms. Then it looks like a lot of people are dying from the disease, right? I mean, a lot of people were dying from the disease, but that inflates the number. There's a bias because you're only testing the people who are sick, right? You're not testing the people with mild symptoms or even with no symptoms.
No, for sure. It's a clear sampling bias.
Yeah. The other bias was some of the people who had caught the virus had not died yet. Right? So you count them as living, but that doesn't mean they survived the disease, right? So that's a bias in another direction. And that's an example where you actually have, a somewhat mechanistic model that's based on the, epidemiology of how a disease transmits and circulates in a population. Then on top of that, you need to build a measurement model to account for, how the data is collected, right? But at the end of the day, none of the, we were not able to draw any conclusions unless we understood what was the rate of people who were symptomatic or had severe symptoms, right? And so there's one parameter in the model, which is the asymptomatic rate. And so now you have two options in a classical statistics framework. Either you fix the parameter, and then you're making a strong assumption, and maybe you try different values of the fixed parameter, right? Or you just say, well, I don't know this, so really I have no idea what the mortality rate is, because maybe the entire population was infected, or maybe only a small fraction was infected, and everyone in that small fraction had the severe disease, right? And so we needed an in-between, between saying we don't know anything and saying we know everything. And this is why I think where Bayesian shines, which is we can quantify uncertainty. We have more nuanced statements through the language of probability about what our state of knowledge is. And actually, what had happened is there were some instances where we had measured an asymptomatic rate. Right? The example was it was a cruise ship, the Diamond Princess, in the coast of Japan. So they had identified some cases of COVID-19. They put the cruise ship in quarantine and they test everybody, regardless of whether they had symptoms or not. Right? So now you have a small population, and based on that small population, you get an estimate of the asymptomatic rate. Sorry. And then you had one or two incidents where people do that. There were some cities where they had done some other experiments and measured some other data. And so then you bring all that information and you use that information to construct priors and then to propagate uncertainties into the model, right? The reason we're able to make predictions and then to calculate things like the mortality rate with the appropriate uncertainty is because we had a prior on the asymptomatic rate. Right? And that's a very nice example. This is more an example of, why it was crucial to have a prior rather than, how should you construct priors in general, right? This is a bit of a specific case, but it's a very good example. And so I'll recommend two papers. One is the one by Julien Rioux, which was, this appeared in PLOS Medicine. And it's with a lot of contributors, but it's estimation of SARS-CoV-2 mortality during the early stages of an epidemic. And then the other paper that goes a bit more into what are the lessons that we learned from this from a Bayesian workflow perspective is Bayesian workflow for disease transmission modeling in STAN. And so here the first author was Leo Grintiach.
Mm-hmm.
And then we had also Lisa Semenova and Julien Rioux as co-authors. Mm-hmm. And this is a beautiful paper that really goes into the, here's the prior we use, here's the first version of the model, here are the limitations with this model, here's how we diagnose the models, here's the next iterations, and we go through all the iterations, right? And I like to throw the number that the model that eventually we used to model COVID-19 was the 15th iteration, right? And along the way, we had a model that took 3 days to run, and we had to change the way we wrote the STAN model to improve the computation. So that had to do with how the ODE was parameterized and how the automatic differentiation was happening. We got it from 3 days to 2 days. And that's useful, 3 days to 2 hours, not 2 days, 2 hours. Drastic speed up. And so that not only was good because the inference was faster, but that's what allowed us to then use more sophisticated versions of the model.
Yeah.
Right? And so all that is described in that Bayesian workflow for disease transmission model paper.
Oh yeah.
So that's my epidemiology fairy tale. And I don't mean that in the sense that it had a happy ending or that everything was nice and glowing. I mean that this is a very nice story that touches upon a lot of interesting themes.
Yeah, for sure. Definitely gonna use link to this paper in the show notes. I already have it on the Stan website. Actually, you've done a case study on this, so that's perfect with all the co-authors. So I'm gonna put that right now in the show notes. And maybe last question before letting you go, Charles. I'm breaking records these days on the episodes. Like, is episode 89 is going out this week actually, and it's so far the longest episode. It's about 2 hours, and right now we're like approaching this record, Charles. So like, well done.
There's a fantastic podcast, and I forget the name. It's a German podcast. I can't believe I forget the name. I'll try and email you what it is, but basically they do interviews with these, intellectuals and well-established, politicians and I'm not saying all politicians are intellectuals, but people who have opinions and thoughts, and there's no time limit to the interview, and they just go on and on and on and on and on, and they just have so many topics to discuss. It's really I'm not saying you should do that with me, but you could imagine, like, for someone like some of the other co-authors that have come up, like, I feel like you could talk 6 hours with them, and you would just pick their brain, and they would have so much insights to share.
No, for sure. Most of the time, the limitation is the guest's own time.
Right. But I think it's really cool, this idea of we're gonna do. What if we didn't have a time limit on the interview? What would happen? And
exactly.
Eventually, somebody gets hungry, and that's what happens. But
exactly. But so basically, before asking you the last two questions, I'm also wondering, because you also teach, so that's super interesting to me, and I often hear that a lot of practitioners and beginners in particular might be hesitant or even intimidated to adopt Bayesian methods because they perceive them as complex. So I don't necessarily agree with that, that underlying assumption, but without necessarily disputing it, what do you do in those cases? Basically, what resources or strategies do you recommend to those who want to learn and apply Bayesian techniques in their work, but might be intimidated or hesitant?
Okay. So I think that usually when I teach, most of the time it's people who are already, interested in Bayesian methods. Especially if it's a workshop on Stan, the people who do sign up, they already have adhered to Bayesian methodology. So I don't know that I've really had to convince that many people. Definitely when I was a TA at Columbia, I had those conversations a bit more with the students. Especially when I TA'd the PhD level course that, everyone has to take applied statistics, and, not everyone is going to do Bayesian, right? And so we have those conversations. But I think that ultimately what it is it's not that Bayesian is complex, it's analysis is complex. Analysis is difficult. And, when you use less complicated methods, like maximum likelihood estimate or point estimate, and these are not simple. I really don't want to undermine the difficulty related to those methods and the fact that they are useful in a lot of applications. But in a way, those methods are simple, and they will work for simple analyses. right? But if an analysis requires you to quantify uncertainty, to propagate uncertainty, to take some decisions with imperfect data, and then someone says, "Well, I don't want to be Bayesian because that's complicated, but I still want to quantify uncertainty, and I still want to propagate uncertainty, and I still want to make predictions." Well, suddenly the classical methods, you really have to do a lot of gymnastic to get them to do what you're interested in. And so the classical methods also become complicated. And that's more because you're trying to use them for, to do a sophisticated analysis. And so I think that what matters is, to really meet practitioners where they are, what is the problem they're interested in, and does is it a problem where the complexity of the analysis would be handled in a relatively straightforward way by a Bayesian analysis? And the answer could be yes. It could also be no. And if it's no, that's fine. I think that again we have to be loyal to the problem more so than to the field or to the method. But that's how I would start this conversation. And so when I'm sitting with pharmacometricians, and by the way, a lot of them don't use Bayesian. I think I can talk for 30 minutes about what do we want to get out of a pharmacokinetic analysis without bringing up what kind of statistics we do. And once we've established the common goals, then we think about what are the methods that are going to get there, right? That's how I would do it. Frankly, I haven't had that much experience doing it, so take what I say with a grain of salt. But I really think Bayesian is complicated because it confronts you with the complexity of data analysis, right? It doesn't introduce the complexity. Let me put it this way.
Yeah. No, completely agree. And that usually is. I usually give an answer along those lines, so that's interesting to see that we have converged, even though we didn't talk about that before the show, so that people don't start having conspiracy theories about Charles and I trying to push back the message.
This is not rehearsed.
Exactly. Awesome. Well, is there a topic I didn't ask you about that you'd like to mention before we close up the show?
No. Let me keep it simple.
Yeah, I mean, we've talked about a lot.
There are a lot of topics that I think we could have very interesting conversations about. But I also think that we're starting to hit the time constraints.
Awesome. Well, let's call it a show then. Me too. I could keep asking you a lot of things, but let's do another episode another day. That'd be a fun thing. Or if one day you have a model you've been working about and that you think would be beneficial for listeners to go through. I have this new format now, which are the modeling webinars, where basically you would come on the show and share your screen and show us your code and do some live coding about basically a project that you've been working on. And so if one day you have something like that, feel free to get in touch and we'll get that organized, because it's a really, really cool new format and I really love it. In August, we've had Justin Boyce showcasing how to do Bayesian modeling workflow in the biostatistics world. And so even if you're not a biostatistician, it's a really useful thing, because basically, as we were saying, Bayes are basically methods. And so even though the field might not be yours, the methods are definitely transferable in the workflow is. So that was a very fun one. And then we've got one coming up in September, in theory, with Benjamin Vincent. And we're going to dive into the do operator, the new do operator that we having PyMC and how to use that. So that's going to be a very fun one too. So
yeah, I love the idea of that format, and I'm definitely going to check out the two webinars. The one that's already there and the one that's coming up. Actually, the two topics sound extremely interesting.
Yeah, I'll send that to you, and yeah, for sure, that's something I've been starting to do. And so yeah, if you have one such analysis one day, feel free to reach out. That'd be a fun one.
Absolutely.
So before letting you go, of course, I'm going to ask you the last two questions I ask every guest at the end of the show. One, if you had unlimited time and resources, which problem would you try to solve?
Oh yeah. I thought about this, and I feel like so much of my work is about working under computational constraints. And time constraints and resource constraints, and suddenly you relax all of this, and I think for me the really big questions, let's say at a curiosity level, right? I think there are they're utilitarian questions and philanthropic questions that I might prioritize. But my thinking right now is I really love the problems I worked on in astronomy. I am mind blown by some of the stuff my colleagues do in cosmology, where they're trying to understand, the early universe. They have models with 6 parameters that apparently explain the entire structure of the universe. I like to understand that, that a little bit better. I love the work I did on exoplanets. I think thinking about, is there life on other planets? How does it manifest? My advisor when I was an undergrad, she put it a good way. She said, astronomy helps us think about our position in the universe, our place in the universe, and if I have unlimited time and resources in this completely ideal scenario, I think I would gravitate towards these really, really big questions. Which, by the way, I can still get involved in right now as a researcher in Flatiron, but it's true that there's more competition for that. And just there's a theme that if I had thought about this more, I would have just started there. But there's a theme that I really like. This goes back to cosmology, to astronomy, which is this idea of a theory of everything and, a very fundamental model. And, maybe it all reduces to one equation or one set of equations. And what I really wonder is, if we did have that model and that theory, how much insight would we actually get from it? Because, you can have a simple system with simple particles and simple interaction rules, and that doesn't mean you understand the emerging behavior of the system. And if I had unlimited resources and I can actually figure out what that equation is and then run the simulations with infinite computation, and then study the behavior and actually, at a very conceptual level, understand how much insight we get out of this. Yeah. And the example I like to give is, the rules of chess are simple, but just because you understand the rules of chess doesn't mean you understand chess. Right? And I think that there is a tension with the reductionist view of physics and the state of the world that we live in, that is kind of related to that. And that sometimes the simplifications that we use, the involvement of probability theory, of statistics, that's still useful, not just because we don't have the computation to run all the simulations based on fundamental equations, but because it actually is more intelligible to us. And I think with unlimited time and resources, you could, really explore that. Right? Once you can run all the simulations you want, what are the actual models that teach you something and that give you insights? So I tried that.
Yeah, That sounds like a fun one, for sure. And second question, if you could have dinner with any great scientific mind, dead, alive, or fictional, who would it be?
I read the question yesterday, and I really have. I like the idea of. That's not a definite answer. Let's put it as an answer. But I like the idea of talking, with one of the, founders of hypothesis testing. So,
Okay.
Neyman, Pearson, Fisher, and and by the way, just because I'm having a dinner with them, that doesn't mean I condone everything they've done and their character and their behavior. Just to full disclosure, but I think that I'd be interested, to ask them, what were you thinking when you came up with those ideas, and what do you make of how this method that you've developed has been used and misused in current days, and what do you, and also like I don't know how much Bayesian methods were on their radar. But what would they think of Bayesian methods now that we have the computations that are available? So kind of, someone from the early 20th, late 19th century, one of those, statisticians that's described as having done something foundational, but also that has worked with, on a field, on a branch of statistics that historically has been opposed to the branch of statistics that I work on. And I think that could be hopefully a pleasant, certainly an engaging conversation for dinner.
Yeah, very interesting answer and very original. You're the first one to answer that, and I had not even thought about that, but that definitely makes sense.
Again, an answer. Like if having dinner with Laplace is on the table, I'm not saying I wouldn't pick that.
Yeah, for sure. But yeah, that's definitely super interesting, and I do remember that I mean, in my recollection, which of course is very fuzzy as any Homo sapiens memory, we talked about that in episode 51 with Aubrey Clayton, and we talked about his book, Burnley's Fallacy and the Crisis of Modern Science. I'll put that into in the show notes. And I seem to remember also from his book that the founder of hypothesis testing definitely had an active role in putting aside Bayesian statistics at the time. That it was definitely very, very motivated also in that regard. But I don't remember why on the top of my head. But so yeah, I'll put that into the show notes. I should re-listen to this episode also personally. That was a very interesting one. So I recommend it to people who, when I get started with the podcast, actually, I think it's a very good first one to understand a bit more, basically why you would like to think a bit more about the foundations of hypothesis testing, and why it's interesting to think about other frameworks and why the Bayesian framework is an interesting one.
Oh yeah, that sounds great. Yeah, so maybe I could have dinner with. Remind me the name of your guest. Yeah, I mean, add that to my answer.
Awesome. Well, thanks a lot, Charles, for taking the time. As usual, I put resources and a link to your website in the show notes for those who want to dig deeper. Thank you again, Charles, for taking the time and being on this show.
Thanks, Alex, for the invitation and also, the service to the community that I think this podcast is. It's really a fantastic resource. So thank you very much.
You had to be a good breezy and change your predictions after